Welcome back, everybody. Today, we are finally going to discuss function fields over C of the modular curves x of n, x1 of n, and x0 of n, which we haven't even defined yet. So let's get started. The yn, y0 of n, and y1 of n from last time, they can actually be shown with a little elbow grease to be Riemann surfaces, which justifies the term modular curve. But you can compactify them by adding in their cusps. Now, a cusp is just an orbit of an action of one of the gamma associated to one of these three curves on Q union infinity. What I mean by that is, pick one of these curves. There's a gamma associated to each one of these, right? The gamma associated to y of n is gamma of n. The gamma associated to y0 of n is gamma 0 of n. The gamma associated to y1 of n is gamma 1 of n, and so on. We know all of those gammas act on the upper half plane by fractional linear transformation. They act on Q the same way. And if you think back to like a calculus 1 class, you can see that they should also act on infinity in a certain specified way. If I take a little gamma in one of those big matrix groups gamma and I act on infinity, well, what would that be? Well, if I naively have it act on infinity by fractional linear transformation, I get A infinity plus B over C infinity plus D. And if you think about how limits at infinity work, you realize this should just be set to A over C, okay, quotient of the leading coefficients. And that turns out to work. Okay, so the orbits of the action of the various groups here on the set Q union infinity, there will always only be finitely many such orbits. So there will always only be finitely many cusps that we can tack onto these open modular curves to produce compactified versions of these modular curves, which we'll call complex modular curves. And those are written x of n, x0 of n, and x1 of n. And it will turn out, it's crucial that we see this later, you can define x0 of n and x1 of n among other modular curves as algebraic Q curves, not just as C curves as we've done here. We're going to have to do that to understand the fivefold theorem fully, because one of the statements, one of the equivalent versions of modularity that we looked at was that there's a certain surjective Q morphism of Q curves from x0 of n to our given elliptic curve. Well, you have to know what x0 of n is as a Q curve, not just as a complex curve. So we'll talk about that in the next videos. For now, let's try to understand the theory over the complex numbers. Let's let phi of t be the Weierstrass phi function, thought of as a function on lattices L sub tau, or as a function of tau if you like. If you haven't seen the Weierstrass phi function before, just see my series of talks on the congruent number problem. It's essentially the bridge between complex tori and complex elliptic curves. Let's let n be a natural number. Let's let v be a vector in Z2 with entries C, V, dv. And I want v bar non-zero, where v bar is the reduction of v mod n. Let's define f v bar 0 of tau to be g2 of tau over g3 of tau. I defined g2 and g3 in terms of the lattice L tau in a previous video, so make sure you get caught up on the series here. Times the Weierstrass phi function evaluated at cv tau plus dv over n. Now this is weight 0, and it's invariant under gamma of n. Okay, and so in other words, it lives in the complex function field of the modular curve x of n. You can see just by going back to definitions of modular functions and modular forms and invariants under various congruent subgroups of SL2Z that these two notions are the same. Okay, now if I look at this new function here, which I'll define to be f d bar 0 of tau, that'll be shorthand for f0 d bar sub 0 of tau, which is one of these guys. I'm basically choosing a special v to be the v equals 0d. Okay, I do want to require one thing though. I want to require that d is not 0 mod n. Okay, and then I'll look at one other function, and I'll just call it f sub 0 of tau. That's just the sum from b equals 1 to n minus 1 of f d bar 0 of tau. Now, these are both of these, they're sums of special cases of the f v bar sub zeros, of course. The first guy is invariant under gamma 1 of n, and the second guy is invariant under gamma 0 of n, and they're both of weight 0. And as I just got done discussing, that means the first guy lives in the complex function field of x sub 1 of n, and the second guy lives in the complex function field of x sub 0 of n. Okay, and finally, you can also pretty easily check that the function, which I'll call j sub n of tau, which is just the j invariant evaluated at n tau, that lives in the complex function field of x sub 0 of n. Okay, and again, j is just the j invariant. We've talked about that over the past couple of videos. Okay, so we've got some special functions here. We've got these f d bar zeros, these f sub zeros, these jn's, these j's, okay? And what these functions allow me to do is very elegantly describe the complex function fields of the modular curves x of n, x1 of n, and x0 of n. Before that, one last definition. Let's let f sub 1, 0 be defined to be f sub 0, or let's say f plus or minus 1, 0 bar sub 0. And let's let f sub 0, 1 be f1. These two things will be the exact same function, and they'll both be f plus or minus 0, 1 bar sub 0. So these two guys are almost the same. You're just swapping the ones and the zeros. Okay, and both of these are just special occurrences of functions I've defined up here. Okay, so major proposition. It turns out the complex function field of x of n, so the weight 0 functions that are invariant under gamma of n, in other words, those just happen to be given by take C and adjoin the J invariant f1, 0 and f0, 1. And boom, you got your function field on the modular curve x of n. Simple as that. How about the complex function field of x1 of n? So these are the weight 0 functions invariant under gamma 1 of n. That's even easier. That's just C adjoin J and f1. And remember, f1 and f0, 1 are the same. Okay. And so we're essentially deleting, let's see. We're essentially just deleting this. Right? And then finally, the complex function field of x0 of n, so that's the weight 0 functions that are invariant under gamma 0 then. That's just C adjoin J and f0. And it also happens to be just C adjoin J and J sub n. And I defined all of these functions above. This is all proven in Diamond and Sherman chapter 7. In fact, a good reference for this talk in general is almost, the entirety of the first several chapters of Diamond and Sherman. The point is, I can very elegantly, in terms of some very sort of understandable functions, describe the function fields over C of all the various modular curves we've just developed. If you want to know what this says geometrically, you can use the curves fields correspondence that I made a video about. And this shows in particular, I'll just pick on x1 of n here. x1 of n is birational equivalent. In other words, it has like a dense open subset that's isomorphic to a dense open subset of a plane curve defined by, let's say, phi sub 1. So that'll be a polynomial in two variables over C, such that when I evaluate phi 1 at J and f1, I get 0. Okay. So birational equivalence in algebraic geometry, that's equivalent to the two curves having the same function field. Okay, so that's what's going on here. And how about x0 of n? X0 of n is birationally equivalent to a plane curve defined by, let's call it phi sub 0 in CXY, such that when you plug J and F0 into phi 0, you get 0. Okay? So you can think of all of this algebraic stuff pretty geometrically. Let's talk about universal elliptic curves briefly. Let's consider tau in the upper half plane as a variable, just so that J of tau, the J invariant of the elliptic curve associated to the lattice L sub tau, is thought of as varying. As tau changes, I want to think of the J invariant as changing. Okay. You can construct an elliptic curve E sub J of tau, which is called the universal elliptic curve, in the following way. We'll call it E sub J for shorthand. It's just y squared equals 4x cubed minus 27j over j minus 1728x minus 27j over j minus 1728. And what's neat about this is that if you plug in tau into j in all these various spots that you see at j, this guy specializes every time you plug in a tau to a complex elliptic curve with j invariant j for every possible j except j equals 0. Obviously, that gives you a singularity. And j equals 1728 is obviously also not possible because you'll divide by 0. So this one big universal elliptic curve can be thought of as like a family of elliptic curves as you plug in the various taus into all the j's that you see here. Okay, and you'll get an elliptic curve with every j invariant you like, except for you won't get one for j equals 0 or 1728. And so it's interesting to take this one big mega elliptic curve that kind of combines all of the information about all the various complex elliptic curves associated to lattices. Combine that into one big curve and you ask, all right, let's ask a simple question about it. Let's let EJ be the universal elliptic curve. Now, what is this an elliptic curve over? I think it's best, given the context we've been discussing within, it's best to think of this elliptic curve as an elliptic curve over the field C adjoin J, right? Because all the coefficients certainly live in C adjoin J. They're all rational functions in J. So you might ask, okay, let's take that base field. Let's take that field and let's adjoin the x coordinates of the capital N torsion of EJ to it. What kind of field do we get? Well, we can certainly say some things. Here's one interesting thing. If you take CJ, the base field, and you adjoin the x coordinates of all the capital N torsion of the universal elliptic curve EJ to it, it turns out you just get the complex function field of x of n. That's pretty wild. So that's another kind of deep connection between modular forms and elliptic curves right there. Function fields of modular forms are tied to torsion fields of the universal elliptic curve. Okay. Let's see. I can also say more though, because I can also ask like, all right, well, it's natural not just to consider this field in isolation, but it's natural to look at it as an extension of C of J, because this is the field over which the universal elliptic curve sits. You might ask like, all right, well, is that a special extension? Does it have any nice properties? Yes, that extension is Galois, and its Galois group is SL2 of Z mod NZ mod plus or minus the identity matrix. Okay, so it's got a very simple kind of understandable Galois group. And you can see Diamond and Sherman chapter 7 for this. But there's a nice quick consequence of this last fact here, which is the last thing I'll say for today. You might ask, all right, what if I take the full torsion field? What if I take CJ, the curve over which my universal elliptic curve, or the field, excuse me, over which my universal elliptic curve sits? What if I add in all of the n torsion of the universal elliptic curve to it, not just the x coordinates? Well, of course, that's still going to be Galois, that field extension. Its Galois group is going to be SL2 of Z mod NZ, basically because if you look at the formula for an elliptic curve, our universal elliptic curve here, to every x coordinate of every capital N torsion point, there will be 2 y coordinates, depending on which sign you choose, plus or minus, attached to the y coordinate. So you're kind of removing this mod plus or minus identity when you move from the x coordinate torsion field to the full torsion field. Okay, so this is a pretty neat little fact, and we'll use this. But what we really want to do is, starting next video, we want to ask, how does all this look if I change the ground field from C to Q? Can I come up with a theory that actually makes sense and that's useful? Can I define my modular curves and their function fields over Q? Can I get meaningful theory? Yes, you can. And I'll talk about that starting tomorrow. So thanks for watching, and I'll see you then.